Hi, my name is Shrikar Lekkala, and today I'll be talking about algorithms, and in particular sorting algorithms, as concept 1.A.4 pointed in the events list. My partner Mokshith Mannuru is not here, so I'll be presenting in his behalf as well. So first of all, when talking about algorithms, we must understand what an algorithm truly is. As an algorithm is a set of steps to accomplish a task or solve a problem. These algorithms can be very simple. For example, a recipe for a Hershey's Easy Pizza Brownie, a peanut butter and jelly sandwich tutorial, or even a range of steps to start a car. How does this relate to technology? An algorithm is a set of steps for a computer program to accomplish a task. These steps need to be efficient, comprehensible, and correct to be able to be put into real-world application. By efficient, I mean the algorithm needs to be fast and space conscious of the device it's on. By comprehensible, I mean the algorithm can be understood by the computer and the human responsible for debugging. And correct, it needs to be able to solve the problem and task at hand. Algorithms become more and more complex as harder problems arise. For example, Google Hangouts uses audio and video compression algorithms to transmit video and audio signals across devices. Again, Google Maps uses route finding algorithms to find the easiest and fastest way from point A to B. This algorithm is more commonly called the Dijkstra algorithm and is very popular among computer scientists today. These are just two different types of algorithms, and there are actually many types of algorithms. For example, sorting algorithms, searching algorithms, brute force algorithms, recursion, etc. But today we'll dive into sorting algorithms and their usage. What is a sorting algorithm? A sorting algorithm is an algorithm that puts elements of a list in a certain order. This can be numerical, alphabetical, or really any way you desire. Solutions can range in complexity and efficiency. For example, a 4-letter list can be put into alphabetical order using a sorting algorithm. And similarly, a randomized number list can be put into numerical order using a sorting algorithm. And while this third picture may look complex, it is actually doing the same thing that the second, more easily understandable picture does in a different way. It is actually called a merge sort. So imagine you're given a set of 15 books and somebody tells you to put them into alphabetical order by author. There are infinitely many ways to look at this task. You could go from first book and switch the book based on alphabetical order of the author until the whole list is set. Really, any way. You could split the list of books into 2 halves and then solve it from there, solve each half and then solve it as a whole. Or you can insert the books where the corresponding letter would point to. Now you may ask, why do I need a computer for this simple task? You see, this is the biggest library in the US, the Library of Congress. It would be very hard for a human to sort these books by alphabetical order according to author. As a human, it would take hundreds, maybe even thousands of hours to do this. A computer may be able to do this within 10 minutes. Now, let's create our own sorting algorithm. The objective is to sort the cards in numerical order when given in randomized order. As our originating algorithms in our first slide, such as the recipe to make the Hershey's brownie, or even the PB&J sandwich, the one thing they have in common is they all have steps to solve the problem. So our sorting algorithm would have 3 steps. Step 1, starting from the first card, compare the card at the next index. So we'll just compare the card to the right of it, if applicable. And then step 2, if the first element is greater than the second element, they're swapped. So basically the value of the first card is greater than the second card, they're swapped. And step 3 is the recursive call, which repeats this process throughout the line of cards. So let's visualize this. We have 4 cards, and I put 4 indexes, starting at 0, 1, 2, and 3 for the 4 corresponding cards. Now, in order to sort these cards do need a value. So I put an 8 for the 8 of spades, 4 for the 4 of hearts, 3 for the 3 of hearts, and 2 for the 2 of diamonds. Now integrating our steps into this, we start at index 0, which is the 8 of spades, and we will compare it to the 4 of hearts. And if the 8 of spades is greater than the 4 of hearts, which it is, they will be switched. And now we go to the 8 of spades and compare it to the 3 of hearts. And the 8 of spades happens to be bigger, so by our steps, we do switch these. And then again, index 2 to index 3, 8 is bigger than 2. As you can probably see, we switch these. And then now, here, what do? By step 3, in our original process, we go back and recursively call to the first index. And we see if 4 is greater than 3, which it is. So what do? We switch it. We switch 3 and 4. And then we go to index 1, and we see if 4 is greater than 2, and it is, so we switch it. And here, the 4 is in its correct position, so the sorting algorithm recursively calls to the index 0, and the 3 and the 2 will switch as due to our first step. Now, we have just executed a bubble sort. By implementing these 3 steps, we have created an algorithm that can be stretched into sorting a library's database of books, or even sorting and creating a schedule for a commercial airline. This is incredible. This is a real code example of a blackjack game I've coded in Java, and it's pretty simple actually. As you can see, there's a swap helper method. And here's our other sorting code algorithms. This one is a selection sort. These all do happen to do the same things, so please don't get too caught up in the complexity of the code. This one is an insertion sort. The one before is a merge sort. And now we have some trade-offs in algorithm creation. Algorithms can be correct, but if they're not efficient, why would we use them? For example, you probably would not use Google Maps if it took 30 minutes to load up and took up all of your phone storage. To solve this problem, Google created an algorithm that was both efficient and storage compliant to suit the consumer's needs. To go from A to B the fastest. The same concept applies to sorting algorithms. All of these algorithms are correct, but not all are efficient in every context. Because of this, we weigh the context of the sort and the space complexity of the sort before using it in a mass productive solution. Insertion sort completes nearly instantly in a nearly sorted list, but completes relatively slow in a reverse list context. If you look at this GIF, you can see once the GIF restarts, the nearly sorted list completes almost instantly, while the reverse list takes a while to complete. Here we have to be careful of where we use the sorts in every context. In conclusion, as technology advances and new algorithms are created, more efficient and usable sorts will be created based off sorts like the one we have employed here, and humans have to effectively weigh every algorithm's efficiency and storage to be applied in a worldwide context. And here are the sources I've used for this presentation. Thank you.